All right, this is 5.3 notes for the sum and difference identities just for cosine. So one of the big mistakes people make is right here at the top. People think that the cosine of A minus B is equal to the cosine of A minus the cosine of B. This is something that's not true. If you look at your unit circle, you can kind of see, I'll show you on, but this is just a little example to show you how that doesn't work. So the cosine of pi over 2 minus 0, well, pi over 2 minus 0 is just pi over 2, so that's going to be equal to the cosine of pi over 2. And then remember, pi over 2, that's an angle that we know about on our unit circle. There's pi over 2. Remember that if I wanted the cosine, that's just the x value of the coordinate there. So I know that the cosine of pi over 2 is 0, and that's it. Now, if I wanted to say that the cosine of pi over 2 minus 0 is equal to the cosine of pi over 2 minus the cosine of 0, which I just told you is not true, let's see what would happen. So we would have the cosine of pi over 2, which we just saw the cosine of pi over 2 is 0, so we would have 0, minus the cosine of 0. Well, here's 0. The cosine of 0 is 1, so we'd have 0 minus 1, which is negative 1. So you see that 0 does not equal negative 1, so that just is an example to show you how the cosine of A minus B is not the same as the cosine of A minus the cosine of B. So how can we evaluate something that's in the form cosine of A minus B? The following identities are called the sum and difference identities for cosine. They're useful in some applications and can help find the exact values of certain functions that are not the angles we already know from the unit circle. So from the unit circle, we're pretty familiar with 30, 45, 60 degrees, the angles that are on here. But if I asked you, say, the cosine of 15 degrees is not on here. But using those sum and difference identities, we wouldn't even need to get a calculator out. We can kind of figure that out on our own. So here's the two formulas. Again, these are on your formula sheet that you're going to have on your test, but you're going to have to be able to use them. So the cosine of A plus B, the identity says that it's equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. It's almost the same exact formula for the difference, the cosine of A minus B, except for then you have a plus sign between the two things. So how are we going to use this? It says find the exact value for each expression. We'll start with this first one, the cosine of 15 degrees. Like I said, 15 degrees is not on your unit circle. But can we find a sum or difference that makes 15 degrees using angles we do know, such as 30, 45, 60 degrees? And sure enough, 15 degrees is the same as saying 45 degrees minus 30 degrees. Now, you might think that's complicating things, but I don't know the cosine of 15 degrees. What I do know is the sine and cosine of 45 degrees and the sine and cosine of 30 degrees by looking at my unit circle. Now, following this formula, this is the difference formula right there, I'm following the pattern. I'm going to take the cosine of the A value, which is 45 degrees, times the cosine of my B value, 30 degrees. And I'm going to need to add the sine of my A value, 45 degrees, times the sine of my B value, which is 30 degrees. So at this point, I can refer to my unit circle again, that first quadrant, and I can see that the cosine of 45 degrees, right here, the cosine of it is root 2 over 2. So the cosine of 45 degrees is root 2 over 2. The cosine of 30 degrees is root 3 over 2. The sine of 45 degrees is root 2 over 2. And the sine of 30 degrees is 1/2. So then to simplify this, root 2 times root 3 is root 6. 2 times 2 is 4. So we've got root 6 over 4 plus root 2 times 1 is root 2 over 4. They have a common denominator, so let's just put them all over that common denominator. Root 6 plus root 2 all over 4. This is as simple as we can get it. We could have put cosine of 15 degrees in our calculator. We would have got some nasty decimal. This is the exact form of it. Exact is always better. All right, so the second example I have here is the cosine of 5 pi over 12. Now this is a little bit more complicated because it's not in degrees, which is what you're more used to. So you have two options here. You could convert it to degrees, which probably most of you will prefer to do. I'm going to go ahead and show you how to do it without converting into degrees. So 5 pi over 12, that's not one of our angles on our unit circle. We see we have pi over 6, pi over 4, pi over 3, things like that, but 12 is not one of the denominators of our radian measures. So I'm going to go up here just to write this out. I want to think of two things that add together to be 5 pi over 12, but I'm going to keep in mind that I'm going to want these to reduce. So 4 and 1, 4 twelfths would reduce, but 1 12th I'm still going to have a denominator of 12. So I'm thinking more in the lines of 2 and 3. So 2 pi plus 3 pi, that's 5 pi. Now I'm doing this because 2 pi over 12, that's the same as pi over 6, and that's one of the values on my unit circle. 3 pi over 12, when you reduce that, that's pi over 4. Pi over 4 is also a value on my unit circle. So I could see that I could rewrite this as the cosine. Instead of 5 pi over 12, I could say pi over 6 plus pi over 4. And then using that same thought process as the last problem, I'm going to use the sum formula for cosine. And this is going to be the cosine of A times the cosine of B minus the sine of A times the sine of B. All right, so then it's just a matter of referring to your unit circle. So try to scoot this in a way that you can see it. The cosine of pi over 6 is root 3 over 2. The cosine of pi over 4, right here, is root 2 over 2. The sine of pi over 6 is 1/2. The sine of pi over 4 is root 2 over 2. So this gets us root 3 times root 2 is root 6 over 4, minus 1 times root 2 is root 2 over 4. Again, this looks really similar to last time. Same denominator, so let's just put it all over that common denominator. And there's no way we can simplify that. That's as good as it gets. All right, so again, you could have converted this to degrees if you wanted to. So remember to convert 5 pi over 12 to degree, 5 pi over 12 to degrees, you would have to multiply by 180 divided by pi. In doing so, you would get 15 pi. So you could have used that to your advantage, found a coterminal angle and worked with that. I totally messed that up. I canceled the 5 instead. So pausing that, we had 5 pi over 12 times 180 over pi. This time I'm actually going to cancel the pi with the pi. That would make sense. So I have 5 times 180, and I divide by 12, and this would be 75, and remember we converted it to degrees. So potentially you could have recognized that that's the same as 45 degrees plus 30 degrees and taken that route if you liked using degrees better than radians. So we'll do this one on the next video. So that was example 1A and B.